Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Digital Holographic Microscopy, that is DHM, from the paper Characterization of Materials 1. So students, let us see what we are going to learn in this module. In this module, the concept of digital holographic microscopy is introduced. Then, the working principle of digital holography microscopy, that is DHM, is discussed in detail in this module. Primary problems in signal processing in a holographic display are discussed. Finally, the advantages and applications of DHM are studied in this module. The field of holography is most certainly mature. It is now over 60 years since Janus Gaber's Nobel Prize winning invention of a new microscopic principle. The term hologram has since entered the vernacular and classical, that is, film-based holography has been used in myriad applications over the decades. The developments of affordable, high-resolution and high-speed digital cameras, along with increased computer processing abilities, have seen holography enter a new phase over the last 2 decades. While the first digital processing of the hologram was performed in 1967, it was not until the early 2000s that digital holographic microscopy started to supersede film-based techniques. Meng et al. Chart the developments from film to digital chip-based holography for micro PIV experiments. In short, digital camera pixels needed to be sufficiently small to resolve micron-scale objects. These cameras needed to have sufficiently fast frame rates for video imaging, and computers needed to be powerful enough to reconstruct three-dimensional electromagnetic fields in a time scale that was deemed useful. These developments drew researchers away from expensive and highly technical film-based microscopes and opened holographic microscopy to a much wider audience. The advantages gained in cost, ease of implementation, and versatility are seen by most to outweigh the loss of resolution in moving from holographic film to digital pixels. Digital holographic microscopy has since been used for metrology applications, achieving sub-nanometer precision along the optical axis to characterize microelectromechanical systems and to image the birefringence of optical fibers. It has been applied to micro PIV applications, examining the time average fluid flow in microtubes and microfluidic channels, and to track a variety of individual micro-objects in fluid environments. It was recognized at the start of the 2000s that digital holographic microscopy could play a large role in biological imaging, and we have seen that DHMs used to study algae, copepods, dinoflagellates, and mammalian cells. Digital holographic microscopy has been combined with optical tweezers and fluorescence imaging. Holographic microscopy has even been used to localize gold nanoparticles inside live murine fibroblasts. Two recent reviews and a textbook dedicated to digital holographic microscopy highlight the importance of this burgeoning and rapidly maturing field. However, despite the enormous promise shown by digital holographic microscopy over the last decade in a diverse range of applications, it is yet to be realized in a meaningful way in the fields of 3D transient flow analysis and 3D microorganism motility. While the aforementioned references show the promise of applying DHMs to understanding the three-dimensional swimming behavior of microorganisms, what has been lacking so far is a way in which to do this quickly and for large populations. Digital holography is an evolving technique representing a new standard for modern imaging applications. The photochemical method of traditional holography is replaced by electronic imaging, thereby opening plethora of capabilities. Even though the superior characteristic features of holography are known since long, however, the application has been precluded due to cumbersome procedures and precise instrumentation requirement. Apart from photorefractive and some special materials and effects, real-time processing is not viable. The interference pattern in digital holography is produced optically when object and reference beam superimpose. The interference pattern is then sampled digitally by using a CCD camera and sent to a computer for further processing. Diffraction theory is used to entirely and accurately describe the propagation of optical fields, wherein the image is numerically reconstructed as an array of complex numbers denoting the amplitude and the phase of the field. The advantages of DH are that it can rapidly acquire holograms. It provides complete information about the amplitude and phase of the optical field, and the flexibility of interferometric and image processing techniques. Thus, by numerical diffraction of optical field, DH allows imaging and image processing methods which are either difficult or not possible by real space holography. Let us discuss about the digital holographic microscopy, that is DHM. DHM is the digital holography which is used in microscopy. It is different from other microscopy techniques which record the projected images of the object. It records the light wavefront information originating from the object as a hologram in digital form. Numerical algorithm can be used to reconstruct the object image. Hence, a computer algorithm replaces the lens used in traditional microscopy to construct the image. The information of the object is fed to a digital image sensor, that is, photodetector, and the image of the object is reconstructed by the computer. Traditional microscopy techniques, not employing a reference wavefront, record only intensity information, while the important information about the specimen is lost. This technique was developed by Dennis Gabor in 1948 while he was improving the resolution of an electron microscope, wherein the correction of aberrations in electron imaging lens became a critical technological challenge. Rather than perfecting the electron lens, he displaced it entirely and found that the complete information of amplitude as well as phase of an electron wave is contained within its diffraction pattern. The optical field is then synthesized optically by the record of electron wave diffraction. Thus, visible light optics could be used for image creation, which was rather simple and matured than the electron optics. Geber termed this imaging principle as holography since it could record the complete optical field. Figure 1 shows the chemical etching, which is measured in real time. Figure 2 shows the DHM phase shift image of cell details, whereas Figure 3 shows the surface finish measurement. Earliest reports to replace photographic holograms in traditional holography with digital recording of hologram and to reconstruct the image by computer surfaced in the late 1960s and early 1970s. Early 1980s saw similar ideas for electron microscopes. However, slow computers along with poor recording capabilities precluded the use of digital holography. By 1990s, computers and the digital image sensors were tremendously improved. However, the required pixel count and density for digital holography still lacked the required standards. The market powering digital image sensors was basically low-resolution videos. 21st century saw the introduction of digital still imaging cameras, thereby driving the demand for economic high-pixel sensors. Additionally, CD and DVD player market has led to the large-scale production of inexpensive diode laser and optics. First reports on the use of digital holography in light microscopy appeared around the mid of 1990s. Nevertheless, the image sensor technology allowing superior quality images could not develop until 2000. At this time, first commercial digital holographic microscopy companies, 4 deep in water imaging and phase holographic imaging were founded. Let us next discuss the working principle of holography. During the holographic recording or reconstruction process, if the hologram is in digital form, then the technique is called a digital holography. During this technique, the optical holographic recording or reconstruction setup is simulated on a computer. Figure 4 shows schematics of the process. Figure 4a represents the process where the object to be recorded is modeled in the computer. After this, the wave propagation from the object to the hologram plane is simulated. These steps are repeated for the reference, after which the interference of object and reference is determined at the hologram plane. In this way, required hologram is formed. Since the hologram is obtained in digital format and is transferred to a photographic film by various techniques such as image setter, optical methods can be employed to develop or reconstruct the photographic film. Thus, this technique allows recording the hologram of objects for which hologram is not optically recordable. This technique is also termed as computer-generated holography and is often employed in making display holograms. Figure 4b illustrates the process in which hologram is recorded optically, but a CCD is used for recording in place of a holographic plate. Therefore, the recorded hologram is in digital format, which can be reconstructed by using a computer. This can be achieved by stimulating the wave propagation from hologram plane to the object plane. The object can be seen on the computer screen. Simulation of wave propagation from hologram plane towards the object plane or vice versa occurs in both the process and is the most important step in digital holography. This is basically a signal processing problem. So, the primary problems in signal processing in a holographic display are: first is the forward problem and another one is the reverse problem. Forward problem involves computing the distribution of light field arising over entire three-dimensional space from the three-dimensional object or feature to be holographed. Conventional holography involves creation of this field via optical methods and then recording by interferometric or other methods. However, digital holography comprises computation of associated fields and is highly complex as three-dimensional features often comprise non-planar surfaces. Thus, wave propagation simulation is fundamental to the working of digital holography. After computing the desired field, physical devices can be used to produce and display it. The field produced by these devices propagates in space and reaches the observer, and it creates the picture of the original three-dimensional feature. Owing to the properties and limitations of these devices, there are several restrictions on the three-dimensional light distribution that can be generated by them. For a particular physical device, example SLM, realization of driving signals to obtain optimum approximation of the desired time-varying three-dimensional light field is difficult reverse problem. Let us discuss the advantages of holography. The first one is the phase shift images. Apart from the common bright field imaging, this technique can also be used to create phase shift images. Phase shift image is a characteristic of DHM and it provides quantifiable information of optical distance. Additionally, the phase shift images can be used to image the topography of an object in reflection DHM. The phase contrast and differential interference contrast microscopes are generally used to view transparent objects, example, living biological cells. However, while visualizing phase shifting transparent objects, these methods often distort bright field image with phase shift information. On the contrary, by creating a separate phase shift image which is showing the optical thickness of the object, transmission DHM avoids distortion of bright field image. Owing to the ability of DHM to visualize as well as quantify transparent objects, it is also called the quantitative phase contrast microscopy. It is highly challenging to study the conventional phase contrast and bright field images of living unstained cells via image analysis software. In contrast to this, image analysis software can readily segment and analyze a phase shift image on the basis of mathematical morphology. Example is a cell profiler. More advantages of holography includes the three-dimensional information. When object wavefront is analyzed from various angles, it becomes possible to completely determine the optical properties of the sample under investigation. Also, the digital autofocus is another important advantage of holography. To achieve autofocus in conventional experiments, the focal distance is changed vertically till a focused image plane is attained. Since a single hologram can be used to calculate the complete stack of image planes, any passive autofocus method can be used to digitally choose the focal plane. Because of the digital autofocusing ability of DHM, it can be used to scan and visualize surfaces very rapidly without requiring any vertical adjustments. By recording a single hologram and then stitching sub-images together, which are calculated at different focal planes, the whole and focus image of the object is formed. Another advantage is the optical aberration correction. Due to the absence of lens to produce images, DHM does not suffer from the conventional optical aberration related problems. Optical aberrations are corrected by design of the reconstruction algorithm. A reconstruction algorithm which truly models the optical setup is not plagued by optical aberrations. Low cost is the another advantage of holography. DHM system includes low cost optics and semiconductor components. Example is a laser diode and an image sensor. The low component cost combined with the autofocusing abilities of DHM result in economic manufacturing of DHM systems. Let us now discuss about the applications of DHM. First one is the living cells imaging. Owing to the non-invasive nature of DHM, it is particularly most efficient in visualizing and quantifying biological tissues and the like. Some of the biomedical applications can be summarized as label-free cell counting and viability analysis of adherent cell cultures. Then, label-free investigations of cell cycle. Then, label-free morphology studies of cell. The second application is surface 3D topography. Analogous to other 3D optical profilometers, DHM performs static measurements of three-dimensional surface topography. It has been applied to a wide range of samples including medical implants, watch components, micro-optics, etc. Third is the time resolved applications. DHM has been employed to study smart surfaces, self-healing surface, non-equilibrium systems, evaporation phenomena, electrodeposition, crystallization, mechanical deformation, etc. Then, an important application is the MEMS. Com drive actuators, micromirrors, accelerometers, gyroscopes, micropumps, microphones, ultrasonic transducers, cantilevers, surface acoustic waves, etc. have been analyzed via digital holography microscopes. Another important application of DHM is the metrology. DHM facilitates accurate height measurements with excellent repeatability as well as good linearity without needing any vertical calibration. It has been employed for accurate positioning of mechanical parts, repeatability of interferometric piezo controller, motorized displacement, etc. Industrial inspection is one of the most useful applications of DHM. Typical applications include implant roughness, structure of semiconductor components, solar industry, industrial metrology, etc. 3D particle tracking forms one of the quite useful application of DHM. A Z-stack of measurement can be reconstructed digitally from a single hologram using a range of propagation distances. For each particle, specific algorithms facilitate determination of distance corresponding to its best focus. This operation on a time sequence of holograms allows determining the trajectory of particles. So students, let us now summarize what we have learned in this module. In this module, the concept of digital holographic microscopy was introduced. Then, the working principle of digital holography microscopy was discussed in this module. The primary problems in signal processing in a holographic display were discussed in this module. Finally, the advantages and applications of DHM were studied. Thank you, students.